Okay, well, here we go. Thank you, everybody, for joining. We just hit 1 minute after the hour, so we're going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. And for those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in conjunction with your microphone and video camera. But we're going to wait until the end of today's talk for taking questions. And so in the meantime, please just do your best to make sure your microphone is muted when you aren't intending to speak. Jeff, I'll go ahead and turn it over to you.
Okay, thank you, Matt. Well, it's my pleasure this afternoon to introduce Nikita Avdievich. And I've been working with Nikita for nearly 3 years on landslide hazards in Alaska. Nikita arrived in our group after working on landslide and rockfall problems in Denali National Park and Yosemite National Park with Denny Capps and Greg Stock. And Nikita started working on our landslide group here in Golden on March 16th, 2020. And I'm being specific about that date because that's the same date that everyone in our building in Golden was sent home because of the pandemic. And even so, during the last 3 years, given those complications, Nikita has managed to be very productive and creative. And much of his focus during this time has been on submarine landslide hazards in Glacier Bay and Barry Arm in Alaska, which is the topic that he'll be talking about today. And with that, I'll turn it over to Nikita.
Thank you, Jeff, and for the kind words in the introduction, and thanks, Matt, for organizing these. As always, I look forward to another good year of good seminar talks. I'm going to turn my camera off here as I get started. I live up in the mountains, and the latency can get a little bit off. But with that, thanks everybody else for tuning in. As stated, this is a talk on submarine landslides and susceptibility in Alaskan fjords. And so generally in talks, I usually like to start with some kind of pretty image of the results in the title slide, but I'm going to try something else a little bit here. So starting with what's above the water first, and this is a satellite view of Glacier Bay in Glacier Bay National Park, which is the subject of most of this talk. And this in particular is a pretty popular destination in the park. A lot of cruise ships visit. I think there's one right there for scale. It's kind of a nexus of a few inlets or fjords that still have tidewater glaciers, which sadly may not be the case for much longer. But I guess I'd like to start my talk on submarine landslide work by stressing the importance of submarine geology. And just showing visually how much we're missing when we're out to do field work in these coastal settings and just totally unable to see half the landscape in this case because it's covered by water. So here's the big reveal, and this is basically just to provide some visual contrast for how hard it'd be really to study and understand a landscape in any context really, while ignoring half that landscape, so to say. So this is now a quick preview of our landslide susceptibility map in submarine sediments in Glacier Bay, which of course I'll detail throughout the talk. I'm going to take this quick opportunity to stand on a tiny little soapbox here just for a second and note that we often treat submarine and subaerial realms as kind of distinct sciences and publish them in different journals. And I think this is a fairly obvious point, but it's a good one to think about. And just to point out that geology and landslides and all the variables that we care about there, so sediment transport, structural weaknesses, gravity, et cetera, none of them stop at the water's edge. And that's not to say that there's no difference. Water is a major variable in how it affects those processes, but in a lot of ways that distinction exists largely because of the difference in the type of data that we collect and then the limitations in the data and the access that we need to study submarine processes. So that said, I think there are a lot of people doing really fantastic work to bridge that gap. And this is especially pertinent in our world of tsunamigenic landslides that many in our group at the USGS recently have been tasked with. So kind of better understanding those coastal slope instabilities. So with that, into some more substantive stuff. What I plan on covering today is a bit of background for context on why we do this work, specifically talking about Glacier Bay as a field area, and then some detail on the submarine landslide mapping we did there. The middle part of the talk will pertain to the actual susceptibility mapping for landslides in submarine sediments specifically, and then we'll end off with some results from Glacier Bay and a bit of an expose on another field area in Prince William Sound, followed by a summary. So I'll start with a couple photos from the two field areas for a little visual context. And on the left is Jeff here standing on the Riggs Glacier Delta in Glacier Bay. And on the right is a shot of Surprise Glacier and Harriman Fjord in Prince William Sound. And of course, the kind of elements that characterize these landscapes, so the ice itself, moraines, large outwash deltas, steep-sided bedrock fjord walls. And I put this definition below for paraglacial landscapes from Ballantyne 2002, which I think very succinctly defines the importance of ice retreat with regards to geohazards. And so what we're looking at is landscapes that are directly conditioned by former glaciation and deglaciation, whereby the withdrawal of that ice exposes terrain that's unstable or metastable and consequently liable to erosion and high sediment release and rates. And so naturally, these geomorphic changes result in pretty landslide-prone terrain. This also involves ecological changes as the climate progresses post-ice, tectonic changes in terms of isostatic crustal rebound. There is still some ice remaining, so ice-adjacent processes like permafrost and its effect on slope failures, especially if it degrades. And then, of course, here we're interested in what's below the water, which very recently was below ice. So that's all to say that these are dynamic and ever-changing landscapes with a lot of unstable slopes of many kinds. And so I don't want to get bogged down in the details of previously published work, but I do want to contextualize this work. And in many ways, the context kind of stresses the importance of submarine analyses more so than any particular individual finding. But this is a sampling of the history of landslide science in Glacier Bay specifically. So many of you know Lituya Bay. It's kind of a poster child for a tsunamigenic landslide. So in 1958, an earthquake triggered a landslide to fail into the water, causing a giant wave that killed 5 people. And I believe to date is still the highest run-up ever recorded at over 500 meters, wave run-up. And so this Miller paper, 1960, details that. And notably, that landslide is the third of 3 known tsunamigenic landslides in Lituya Bay. Below that is Tidal Inlet here, which is an incipient landslide in Glacier Bay proper with kind of, let's say, catastrophic potential if it were to fail. So Jerry Wazorek and many others did a lot of work on this slide in the early 2000s with a bit of preliminary tsunami modeling. And then more recently, our very own Jeff Coe here in our group and Aaron Bessett-Curtin investigated rock avalanches and their recent increasing prevalence in Alaska. And so a very notable one on Lamplugh Glacier in Glacier Bay happened in 2016. And that drew quite a bit of attention. It was about 50 million cubic meters, which is actually about the size of the Lituya Bay 1958 landslide. And it ran out about 10 kilometers, not reaching the coast by another 9 or so. I should mention Tidal Inlet is estimated at around 5 to 10 million cubic meters. And so all this, in my view, kind of culminated in a paper in 2019 in Alaska Park Science, where Jeff and company took kind of a first stab at addressing this question of tsunami hazard, based here specifically on where landslides could theoretically reach the water if there were landslides, but nonetheless a more systematic and more regional approach rather than focused on an individual landslide. And so this ultimately led to a kind of more formalized plan between the Park Service and the USGS to devise a trajectory to study and address this problem. And so the details and the logistics aren't too important, and I'm not going to focus on that. But I think, again, the context is because what's needed for this type of problem is an approach from many sides, addressing different types of landslides, both above and below water, and then using the tools that we have at our disposal to finally integrate that to inform that hazard and that risk. So these colored elements are basically what's been accomplished, or in the light colors is in progress to date. And the tasks are generally split into subaerial landslide mapping and eventually susceptibility modeling. In the middle, using INSAR that our colleagues at Southern Methodist have done some great work on to detect active slopes and problem areas to then hone in on. And then in the blue, the subject of this work, which is to map and understand submarine landslides. And so down the line, these components should be integrated into some form of joint susceptibility map, which ultimately helps us then identify the sources of hazards for tsunamigenic landslides, and then model that tsunami potential. So to get into some actual Glacier Bay information, the park is located down here in Southeast Alaska, kind of sandwiched between the Fairweather Fault, which separates the North American and Pacific plates, and the very southern extent of the Denali Fault on its eastern end. So it's a tectonically active area. It's also visited by hundreds of thousands of people in cruise ships and tour boats every year, and it's really just a magnificently beautiful place to work. It's also pretty novel. It's a pretty novel environment with a good collection of data compared to similar places, at least in Alaska. And so coming from a subaerial landslide mapping background myself, for those used to high resolution SFM or LiDAR data for their geomorphic mapping needs, it's good to note, I think, that there's still a pretty big gap in the resolutions and the kind of ease of getting bathymetric data. So spatial coverage and frequency of data collection is often more limiting in submarine settings. With that said, today's multi-beam sonar bathymetry is miles ahead of what it used to be with our single point soundings, but it can still take days, weeks, months, in some cases years to cover larger areas. And as with most things, it's not cheap. Another point, because the distance from the ship to the seafloor is dictated by water depth, unless you have a submarine, the resolutions can vary quite a bit. So in Glacier Bay specifically, we're looking at sub-meter for some near coastal areas to about 16-meter resolution in areas that are thousands of meters deep. Hundreds of meters deep. And then the bathymetry that we used covers most of the bay. So that's about 80% of the 1,200 square kilometer area. And that was collected in two parts with about an 8-year gap. So that disparity is just another element to address in any analysis. And then I should say multi-temporal data sets, bathymetric data sets are still fairly rare. And generally when they do exist, they're focused on smaller targeted areas rather than kind of a regional picture. We do have a bit of that for Glacier Bay as of a couple of months ago, but unfortunately haven't really had the chance to sink our teeth into that yet. But on top of all that, the entire bay in its current iteration has basically formed over the last 2.5 centuries. And that's as tidewater glaciers retreated back up to about 100 kilometers total from their mid-1700 extent. And fortunately for us, we know a significant amount of that glacial history because it's been documented, mostly through direct observations, but also in some places supplemented with tree ring counts. But all in all, I think it's just pretty cool to use observations from early explorers. So this here is a cartographic masterpiece from Captain Vancouver when he visited in the 1790s producing this. And then many other notable names, the likes of John Muir and G.K. Gilbert, and other USGS and Park Service folks through the last century, all providing a good deal of temporal constraint for the ice and therefore the age of the submarine landscape, at least as far as its geomorphology. So this also includes photos and sketches. I'm not going to dwell here, but it's always nice to see a little historical context. So this first image is the same location as my title slide, but in 1894, when those 3 glaciers were right there at that junction. And then finally, continuing on the topic of Glacier Bay setting, but a slight diversion here, it's good to also take a look at the earthquake data for Glacier Bay back into the record, and specifically with the question of earthquakes, as we know from previous events, being a really important trigger for both subaerial and submarine landslides. And what we find is that there's a pretty consistent history of regular shaking. So the top plot simply shows the major known earthquakes dating back to about 1900 with magnitude on the y-axis and colored by distance from Glacier Bay. But then if we consider the distance and the magnitudes necessary to produce landslides, so for that, for example, here's the Kiefer 1984 envelope. So this plots magnitude against the maximum distance for that magnitude that would still shake the ground to the point of potential slope failure. So we can plot kind of an estimate for relative shaking effect of each of these earthquakes on Glacier Bay specifically. So we divide the distance of the epicenter from Glacier Bay by the maximum distance that that magnitude of earthquake could potentially produce landslides. And so this gives us a better picture that earthquakes within that envelope, so everything above this dashed red line is everything in the envelope, as landslide inducing triggers are pretty regular and abundant. So the Lituya Bay earthquake is circled here for reference. So to jump into some actual landslide work, to start off any landslide susceptibility assessment, you need a map of landslides. So we use the bathymetry, working mostly with red relief as a visualization. And I find this is a nice way to just highlight landslide scarps and deposits in kind of low to medium resolution data. So for those not familiar, this is basically a way to combine an index for convexity or concavity in grayscale here with an index for steepness or slope angle in red. And this produces something that looks like superficially like a hillshade, but it's a bit more quantitative than arbitrary light values based on a sun angle. And I just think works nicely to accentuate the various parts of a landslide, which kind of occupy the different corners of this color space. So for example, steep concave scarps or more flat-lying convex deposits. So using this, we manually mapped just over 7,000 landslide scarps. So because sediment mobility underwater is quite high, deposits unfortunately don't really stick around long, or they get mixed into lobes and fans. And so we use scarps as basically a proxy for landslide locations. We did also map fully discernible landslides, so source and deposit, and that includes both subaerial and subaerial to submarine slides, as well as fully submarine slides, but those don't really paint the full picture in this setting the way that scarps do in terms of their numbers and distribution, at least. So take a quick journey around the bay and look at some visual and examples of landslides. So this is just a good overview of some of the more developed, geomorphically developed post-glacial bathymetry down here in the Central Bay. I think it's a good spot to see the striking visual density or the concentration of scarp features in some of these areas. So in this view, I should note that these look pretty small, but we limited our scarp mapping to about 50 meters across the flanks. So that was kind of a discernible size for the resolutions of our data. And then I'll just point out that 50 meters for a scarp is fairly small when it comes to producing a tsunami wave, but it isn't exactly a landslide that you just accidentally walk over on a stroll without noticing it. I like this spot in the east arm. This was deglaciated sometime in the early 1900s. It's a nice example to point out a couple things. So you can see the different resolutions at different depths, some resulting artifacts in the stitching of the bathymetry, the different texture of bedrock and sediment and how that shows up, and then what some of the scarp mapping looks like in contrast to the more rare, fully defined landslide here on the left, where you can see both the deposit and the scar. And then this on the left is just an annotated version of the same location. So to point out that the relative sizes of the scar and the deposit, the source of the deposit, don't look very congruent. And again, a lot of that material is probably dispersed, buried, mobilized in the form of turbidity currents that travel much further than this blocky nearby material. And then on the right, on the other side of the bay, in the west arm, are some examples where you can see evidence of deposits. So here labeled as turbidite lobes, but really could be subaqueous debris flows and a mix of different material. But you can see that it'd be pretty hard to really trace back this kind of deposit to a single scarp or source area. I'd like to run through some examples of other types of landslides that don't necessarily make it as inputs into the susceptibility mapping, but I think are just great examples of moving ground at this coastal interface. Again, a lot of this work is meant to kind of bridge the gap between submarine and subaerial data. And so that means finding evidence of past landslides that failed into the water. Our susceptibility map is ultimately specific to fully submarine landslides in sediment, and that's because that's what we have data for. But there's a lot that we can also learn and see through just descriptive and qualitative observations using the bathymetric data. And so on the left here is a really well-developed canyon in Queen Inlet here, which is fairly novel for Glacier Bay. Because it's such young terrain. It has a large turbidite fan at its outlet. And turbidites themselves don't generally cause tsunamis, but the landslides that mobilize that sediment in the first place do. And so the Queen Inlet Delta in the background there is one of the more impressive and extensive ones. And the INSAR work that I mentioned actually showed evidence of subsidence there. So it's not exactly a stable and well-consolidated feature. On the right here is this pretty large landslides, several kilometers long. Apologies for the lack of scale bar, I just realized. But this is at the southern end of Glacier Bay called Point Carolus, and it's basically in moraine material from the further extent of the ice. I think it's kind of just a really cool one. You can really see the scarps in the LiDAR and the kind of waveform features propagating back, but in the bathymetry, you can tell that it's likely contemporaneous with the ice being there because the iceberg plow marks overprint the deposits. And so the calving front was still nearby after its failure. And this also raises a, I think, important point of ice as a trigger itself, which has been documented. So calving events. And of course, that's an example of a trigger that disappears. So the conditions causing landslides to some degree change over time in these environments. And then finally, Tidal Inlet is worth a look to see that at least that there's no submarine expression of the landslide. There are several other smaller features along the smaller failures along the edge of the inlet further down here in blue. I'm not going to dwell much on this one, but it is a major player in the kind of incipient landslide hanging over the water territory. I think it's also just a good time to mention, looking at the bathymetry here, that the subaerial distribution of landslides is not necessarily going to mirror the submarine distribution. So having a firm grasp of both to get a better picture of where to focus future tsunami modeling could be important. Okay, so with that, I'm going to jump into detailing some of the actual susceptibility work. So a quick introduction, probably more of a reminder on what susceptibility is and what controls it, but I think worth restating here for this context. I like to think of susceptibility as kind of a lower order map relative to hazard, in that it looks just at the spatial probability, so sort of the inherent properties of the slopes in their propensity to fail, and doesn't explicitly at least take into account landslide magnitudes or temporal probabilities, for example, the timing of triggers. And generally, the most common variables that we think of having a first order effect at least are usually basically how steep is the slope and how weak is the material. So slope angle is fairly easy to get from a DEM. And then broadly speaking, the various things that can go into material properties, which can be also much harder to get. And that could be grain size or angularity for sediments, or the rock strength and the fracture density in bedrock. I've conspicuously crossed out some other variables here that can be important elsewhere, but don't really matter as much underwater. So seaweed roots aren't holding down slopes, to my knowledge. We don't have mer people making road cuts and farming. And then as far as hydrology goes, everything's basically 100% saturated 100% of the time. And so in some ways, the problem is simplified in the submarine environment, but we are also limited in how much we know about the distribution of these variables. And so what inputs do we have then? Of course, we have the map of scarps, effectively our inventory. And most susceptibility maps generally follow the method of taking distributions of these variables, correlating those with the locations, the known locations of landslides, and then you can induce the future locations of landslides based on that correlation. Alternatively, if you do have a ton of landslides, the concentration of those features should be some indication of where future landslides will occur. So at some point, a large enough and a very complete and consistent landslide inventory in a way becomes a susceptibility map in and of itself. And that would implicitly take into account all the variables like substrate types that we can't necessarily determine here. That's also assuming that the occurrence of triggers is fairly consistently distributed in time and space. So for example, you don't have a situation where one side of the field area is constantly getting shaken while another is somehow totally tectonically stable. And generally, at least at these spatial scales, that wouldn't be the case. Other things we can look at in the absence of substrate maps are geomorphic features that we know would have implicitly different material properties. And then finally, at least here, we can also kind of tune our inventory map or our map of scarp concentrations based on temporal constraints from that glacial retreat. So that's kind of the basics of the data that we have, and the goal is to find a way to combine that. To kind of summarize, we have good data for the data that we do have, but we don't have the luxury necessarily of many different variables to throw into a statistical model. I'm not going to hover on this slide, but for reference, this is the flowchart describing how we use those inputs and combine them, but I'll just walk through the different elements kind of visually in order. So first, a little data housekeeping of sorts. We start everything by assessing the completeness of the scarp inventory by looking at the size frequency distribution of the landslide. So in the top plot here, for example, scarp length versus frequency. As with many things in nature, landslides follow a power law in their size frequency plot, and ours is no exception. So there are different methods. We like to use the maximum likelihood estimator method, which is nice because it simultaneously determines a validity domain that gives us a minimum cutoff for the size of scarp that fits that power law. And basically, to be sure that the spatial landslide distribution that we use to then map susceptibility is more complete, we don't use anything below the size cutoff. There's some debate as to what causes the cutoff, whether it's human undersampling or physical processes, for example, smaller scarps getting incorporated into larger ones. For us, it doesn't really matter here. What we care about is doing our best to eliminate landslides that are less likely to be part of a complete inventory. We also estimated minimum source areas depicted here, which we do by systematically connecting the scarp endpoints and then calculating that included area. This is fairly crude and imperfect, but with a large number of landslides, it averages out major differences. And so we get a source area cutoff of about 10,000 square meters. So all that to say, filtering down the inventory helps ensure that fewer landslides are missing from our analysis. And so we cut about 7,000 or so scarps down to just under 1,000. Another important consideration is that the exponent of these fits should fall into the range of other landslide inventories. So we're not just looking at tons of glacial potholes in really coarse data, for example, and they do and we aren't. We also estimated volume of each source area by fitting a second order polynomial surface to each scarp and then differencing that against the bathymetry. Again, this is a pretty coarse estimate that results in some erroneous volume gain shown here with negative thicknesses, but it gives us a sense for the volumes and the thicknesses that we're looking at for these landslides. And then as a final point, in addition to the larger slides being more likely to stick around in the bathymetry for us to observe, another added benefit of cutting out the smaller stuff is that we're focusing more on the ones that are more likely to be tsunamigenic. So wave height is not a simple calculation from just landslide volume alone, but the largest of our mapped slides, somewhere around 1 million cubic meters, is statistically speaking where we get into wave heights about 0.5 meter or so, and that would be noticeable at least to smaller boats. So jumping into the topic of substrate and what we can or can't do with this pretty important control on failure potential. So for example, with lithology, even though we have subaerial geologic maps, interpolating those across a big body of water is going to be pretty speculative. And then in these tidewater glacial settings where sediment yields and transport is really high, we can never really be confident that the underlying lithologies are necessarily indicative of the overlying material properties of the submarine sediment. So in other words, sediments move around and get mixed up. And so to start to get at that question, one thing we did is map all of the fans and the fan deltas in the bay. So basically any prograding sedimentary feature that has a strong submarine expression. And In the future, moving forward, work should be done characterizing these sediment packages, so to assess them in terms of their susceptibility based on things that we can measure: geometry, size, grain size, catchment lithologies, etc. But at this state, we effectively treat fan deltas as a geomorphic feature, known a priori to be oversteepened, unconsolidated, and then most importantly, historically prone to failures, and especially in earthquakes. So as an example of that, in the other field area in Prince William Sound, during the 1964 magnitude 9.2 earthquake, the Good Friday earthquake, most of the damage that devastated the towns of Valdez, Whittier, Chenega, and Seward followed tsunamis that were related to the earthquake, but were directly caused by submarine or nearshore landslides in old moraines and large deltas, especially fjord head deltas. So for example, the Muir Glacier Delta here, to take a look at that, things to note are that it has a very steep front, first of all. It's extensive, it has a lot of fine sediments, at least compared to other things in this area, which are generally pretty coarse grained. It's a very proximal and young landscape. And then all that is also complicated by the fact that for most of these large deltas, you also get superimposed debris flow fans and alluvial fans that contribute another source of sediment. So you can see that in the superficial grain size distribution based on pebble counts that we did, where it's kind of bimodal. So the glacier retreated through here sometime around 1980, and you could see how fast this fan on the bottom has grown over 30 years. And similarly, with this really fast progradation of the glacial delta, a lot of studies have also suggested that rapid accumulation and loading can elevate pore pressures and cause failures, so by burying some of that porosity, basically. But also, because of how fast that material gets filled back in, we don't often see evidence of landslides in the delta fronts, even if we know that they occur. So especially in a single time slice of bathymetric data. So the deltaic slides occur, but are very likely missing from our record. So another important consideration using the scarp inventory. And so finally, the last thing kind of broadly related to material properties, as I said, what we have data for and what we're interested in is slope failures, specifically in submarine sediments. But to actually assess this, we need to split the bathymetry into exposed bedrock and sediment covered surfaces. So to do this more consistently than manual qualitative mapping, we came up with a simple morphometric model, and that's based off of 3 variables. So first, slope angle, taking slopes above an angle of repose to mean consolidated rock. Second, terrain roughness as a proxy for bedrock outcrops tending to be rougher. And then convexity and concavity as a kind of proxy for ridges and basins. So all easily definable properties of the DEM. Here in blue is an example of what we mapped as bedrock using the co-occurrence of those variables. And I think it works as a very much needed first order estimate. And an important thing to note, just to reiterate, this doesn't serve to distinguish material properties of sedimented areas. It just allows us to estimate the total sediment cover, which is needed to properly spatially normalize scarp concentrations, for example, which I'll get into. So the next step to touch upon is correlating submarine landslides with their slope angles. Again, slope is a very often used first order control on landslide susceptibility. So we assessed how frequently landslide scarps in Glacier Bay occur at different slope angles. As far as getting the original pre-failure slope angle value, we found that calculating the slope within a buffer above the scarps produced the cleanest results, but we did also do this with the scarp polynomial surface fits that I mentioned earlier, which gave us very similar results in the end. So the middle plot here is the landslide slope distribution, which we then normalize by the bathymetry slope distribution to get the concentration. And in doing so, we don't include bedrock areas or the fan deltas that I mentioned because those areas don't contribute scarps to the inventory. And so the third plot here is that ratio in log form to more evenly scale those results, linearly scale. And so the couple takeaway points here. One is that submarine landslides occur down to much lower slope angles than subaerial ones. So in our case, down to 2 degrees, below which we don't find any landslides. And this is a pretty frequently corroborated observation in submarine settings, which I think has some important implications for the somewhat conventional idea that we should mostly be concerned about steep slopes. There is a general increase of landslides with steeper slopes, but that more or less kind of flattens out at about 10 degrees or so. And there's this dip at higher angles that I think can mostly be explained by 2 things. One is that we get into a bit of a preservation issue, so scarps from steeper failures potentially not persisting in the bathymetry as much for us to observe, so they might be getting overprinted by new landslides, the concentration of those landslides on the steep slopes being very high. But also there's just a lot less area at those steeper angles in the bathymetry itself, which increases that uncertainty some. So ultimately, this final plot is effectively our slope-based susceptibility index, which we can just use to map slope angles to their relative propensity to have landslide scarps, in other words, susceptibility. So finally, and I think kind of the neatest part of all this is using the maximum age constraints from our glacial extent map to better understand our scarp distribution and use it to map susceptibility. And so a simple way to phrase this maximum age constraint concept, illustrated with this cartoon up here, is that given similar background susceptibility conditions, which we generally expect on average in the same overall field setting, the older an area is as far as when it was uncovered from ice, the more landslides it should have, again, on average. And so between known terminus positions here on the left in dark blue, we interpolated annual deglaciation bands using a spline fit. These are just some close-up examples of that. We did apply uncertainty to all of this in the final calculation, so the exact shape of the glacier terminus is not always realistic, but the concept is basically that for a landslide in a given band, the earliest that it could have occurred is the maximum age of that band plus or minus some uncertainty. And so effectively what we're doing is taking the spatial concentration of landslides shown here, and then adjusting that for how long each area has been deglaciated and thus able to accumulate scarps in that area or band. So assuming, again, average uniform background triggering conditions, the total number of scarps is a function of susceptibility conditions and of time. And we're basically trying to pull out that time variable to get at the background susceptibility. And again, the more landslides you have, the better that signal is theoretically going to be. And so once we normalize scarp area for total area, which is these 2 plots here, so more total area exposed also means more area for landslides to occur, and we remove this effect. And then for these calculations, again, we remove bedrock area and deltas because that area doesn't contribute to the inventory. But then we also remove some of the effect of slope dependence on this metric by not using any terrain that's under 2 degrees where we saw no landslide. So we're looking at scarp concentrations within generally susceptible terrain. And what we find is exactly what our original concept predicts, which is that in areas of the bay where one would expect this hypothesis to hold up in terms of similar background conditions, so for example, the west and east arm, more fjord-like environments rather than the South Bay, we find an increase in landslide concentrations with deglaciation age. So you might notice that this kind of falls apart a little bit in the southern portions, like I said, but these are largely flat-lying with fewer landslides, and then some of the edges are missing from bathymetry, which causes some bias as well. And basically, because this is an exercise in relative landslide concentrations, we chose to tune the fit to areas in the north, which are more susceptible and more concerning areas, effectively calibrating that result to show smaller differences there rather than in the south. But the way we exploited this trend, technically speaking, is basically any deviation from the expected landslide accumulation rate here. So this dashed black line is an indicator of an above or a below average susceptibility to the type of landslide in the inventory. So This brings us to some results and our two individual susceptibility index maps, which I think from a technical perspective appropriately stand alone because the question of how to weight them is a hard one to answer. But in the absence of a clear way to determine that, and in the spirit of creating kind of a single product, the final map here is an additive, equally weighted composite of those three maps. So it's kind of a reasonable one-stop shop deliverable product based on the knowledge that we have. So fan deltas are added back in as areas known to be prone to failure, and then the inventory and slope susceptibility maps contribute information at kind of different scales, one regional and one more slope-wide. Generally speaking, the map shows, kind of pretty unsurprisingly, that susceptible areas are those that have high relief and high sediment input. So thick sediment packages that are often, but not always, oversteepened lead to more landslides. One interesting slight variation on the inventory analysis to actually use the glacial time constraints and then invert the concentrations to estimate a recurrence interval. So here for landslides above our threshold of 10,000 square meters, which would correspond to a rough volume of 10 to 20,000 cubic meters based on the thicknesses. And this, again, wouldn't include the delta since we don't have that data. Overall, the results look similar to the susceptibility map since they use the same data, and I would certainly take the absolute time values with a bit of a grain of salt, since I would imagine those would be pretty sensitive to missing landslides from the record. But it gives us a decent view of where frequent events occur, and an overall sense also that we're not looking at really catastrophic tsunami-inducing submarine landslides on a regular basis here, which is also fairly apparent from the fact that we don't find evidence for those in the 250-year record, but this is a good systematic and visual depiction of that. Another interesting result is that areas of higher susceptibility seem to correspond, in many cases at least, with areas of faster glacial retreat. And so this map shows the average rate between observed glacier terminus positions. So this isn't necessarily causal, and more likely it's just a result of a common variable, which is depth. And basically, tidewater glaciers lose most of their mass through calving rather than through ablation, and then calving scales with depth. So glaciers retreat faster in deeper water. Deeper water also has higher relief and more space to accommodate thicker sediment sequences. And so I think an alternative question arising from this is simply how could we get at the total amount of sediment that is available to fail, which could be a first order predictor of submarine landslides. One probably pretty conspicuously missing variable in all this is the thickness of sediments. There's a difference, of course, between a thin layer of sand mantling some bedrock and a thick fan that's been accumulating for centuries or even millennia. And so this is where seismic data would really come in handy. And this also kind of leads a little bit into the next part, which is similar work that we're attempting to do in Prince William Sound. There we're missing some of the sheer scope of preserved landslide scarps, and the longer timing of glacial retreat isn't quite to our advantage, but it's an older landscape which raises some interesting questions as well. So more specifically, Barry Arm is the area in question in the northwest of Prince William Sound, which is about 600 kilometers to the northwest of Glacier Bay itself. Barry Arm is about 50 square kilometers, so it's about 5 to 10% the size of Glacier Bay for reference. And then the real driver for this study area is a massive incipient landslide, another one, the Barry Arm landslide, which you may have heard quite a bit about recently, but it's kind of an analog to tidal inlet, but possibly a couple orders of magnitude larger at a potential 500 million cubic meters. And so in 2020, NOAA collected detailed bathymetry with an average 4-meter resolution, which is better than in Glacier Bay. And using that similar exercise in mapping, again with the red relief map, we produced a map of nearly 1,000 scarps here with the better resolution. But notably, I'd say that the big striking difference is the number and the size of deposits that really show up in these data. So again, it's hard to tie those to specific sources, but we can at least look at the total area of those. And so as far as repeating the same temporal analysis here, it really doesn't work quite as well. And the big reason, like I said, is that this is a smaller area that was deglaciated slower with fewer known time constraints. But taking a similar glacial temporal perspective does reveal some interesting things. So Barry Arm was deglaciated over the last 2.5 millennia rather than 2.5 centuries. And unlike in Glacier Bay, this left behind 3 prominent moraines. You can see well in the cross section here, which allows us, with ages that we know, and that allows us to subdivide the field area into 3 zones representing about an order of magnitude of time difference. So about 10, about 100, and about 1,000 years on average since ice retreat. So this isn't quite an annual deglaciation map, but we can still look at kind of broad averages. And what we find here is that the general concept stands, that the morphology of the oldest area is a lot more geomorphically developed with a lot more landslides. But in terms of the number of scarps and deposits that we've mapped, we're not getting an order of magnitude more landslides in zone 3 than in zone 2 as per that age difference. So certainly many previous landslides are lost to time. But we do see an interesting trend in the bedrock sediment distribution where the younger zones have proportionately more bedrock. And in those areas, we're subsequently more concerned about bedrock failures, whereas in the older zones, we have more sediment, and I would wager much thicker sediment. So I think this all that to say that this raises an interesting question that brings us back to the paraglacial idea, and that is, to what degree does a susceptibility map, like the one we produced in Glacier Bay, indicate conditions into the future in these changing and dynamic landscapes? So for example, in other words, how much do the last 250 years in Glacier Bay tell us about landslides in 10 years, and 100 years, or in 1,000? And that's kind of the framing hypothesis that I think, looking at a similar fjord setting, such as Barry Arm, which was deglaciated much earlier, suggests that susceptibility to bedrock failures may stabilize over time, but that doesn't mean that susceptibility to landslides and sediment does. It may increase in some cases where the sediment input continues. So we followed a similar frequency size analysis. There's a smaller range of sizes in our scarp inventory. I think I'll leave that here in the interest of time. And in general, again, the older landscape and this less established glacial history in Barry Arm makes it difficult to replicate the entire Glacier Bay method here, but we can still use the variables that we do have. So for example, slope angle, to take kind of a cursory look at the data. In all regards, the results are pretty similar, but there is some evidence that we're missing more higher angle failures. And then applying that same slope index technique for a first order spatial distribution of susceptibility, based again on slope alone, we do see more susceptible area in this older sediment-rich zone, potentially. So more interestingly, I think, with the better bathymetric resolution is just to take a look at some examples here. So the youngest deglaciated zone is where you'd expect bedrock failures, such as this wedge failure across from Barry Arm itself. You can see how it shows up in the bathymetry. In zone 3, conversely, the oldest with the most sediment development, this is a good example of an active fan delta with landslides at its base. So again, this is important because it's evidence of failure in fan deltas, where, for example, in Glacier Bay, we didn't see much of that, with that sediment replenished as the deltas prograde, covering up the history of previous failures. And then as far as examples, I'm going to end off here across the fjord, still in zone 3, and show this large blocky deposit with lots of evidence of failure in this moraine delta complex, despite the coarse grain material and the huge range of grain sizes. But kind of coming back to the broader purpose of integrating the higher resolution bathymetric data with topographic data so that we can map out past events in better detail. As a final thought, I think it's just pretty notable that we've yet to really find clear evidence of previously undiscovered large subaerial deep-seated bedrock landslide like Barry Arm in the bathymetry, which of course is not proof of absence, it's just absence of proof, but we do see lots of evidence of past submarine failures that we'd have no idea about without this tool, and probably many more to be revealed as we get more bathymetric data. So that leads to a brief mention of some future directions that I think this kind of research should take. A lot of it, let's say, is easier said than done because it requires a kind of more data, better data, please request. But I think there are a few areas to aim efforts. One is certainly more work on fan deltas as seemingly the most likely source of submarine landslides, especially co-seismic ones. It's tough without geotechnical data to understand them from a process perspective. I think simple point counts or pebble counts that we've done literally only graze the surface, but I certainly think, at least as a starting point, a statistical approach of some sort could be a huge benefit to evaluate many such features across Alaska and find common threads between deltas that have failed and those that haven't in major historical events, for example. Secondly, I think a better understanding of subaerial bedrock landslide susceptibility. So here are some images of the rock mass characterization work that we have done as a part of informing that. And as far as submarine landslides go, this would also be useful as a means to extend that information underwater to get at the submarine bedrock landslide potential. So basically, susceptibility maps don't have to stop at the water's edge and could take into account bedrock slopes continuing underwater. And then truly on the more data and better data request, which I make slightly in jest, I think there will be a lot more bathymetry available in the coming years, and a lot of it in new places. And if some of that is also multi-temporal and perhaps even supplemented in cases with seismic data, all of that will go a very long way towards a better understanding of landslide recurrence in these environments. And so with that, I'll end off on the summary slide. Just to recap very quickly, how am I doing on time here? Yeah. First, just to generalize a little bit, I think bathymetry reveals a lot of important information and often unseen information about coastal and submarine landslides. Secondly, in these young fjord settings, and especially with good ice constraints, the frequency of landslides underwater and how long they get preserved allow us to extract susceptibility information from the bathymetry, at least to estimate it. And then finally, as a broader point, again, paraglacial landscapes have these changing and dynamic conditions that it's worth considering that landslide susceptibility might stabilize with time as the landscape, quote unquote, equilibrates post-ice. But especially insofar as things like fan deltas failing, that susceptibility could increase with time, which should be naturally accounted for in hazard assessments. So with that, I will leave off on my references for anyone in need of some light reading, and happy to take questions.